In this talk, I'm going to dive quite deep on a specific aspect of SageMaker, and namely the built-in algorithms, which I believe are a very interesting way to apply machine learning, even when you don't have a lot of machine learning skill. Okay, so let's get started. So just in case you missed the first session, I just want to remind you that SageMaker is a collection of modules that you can combine or that you can just pick, just pick whatever you like in there. So we start with notebook instances, fully managed instances, pre-installed with everything you need to do machine learning and deep learning, and the interface to those instances will actually be a Jupyter notebook. Then you have multiple options for training. You can pick from those scalable machine learning algos that I will present in a minute, or you can pick a pre-built environment for Python, TensorFlow, MXNet, etc. And it's very easy to train at scale without managing any infrastructure. Okay? Then you can deploy in a very similar and very easy fashion as well. Just deploy your model behind an HTTP endpoint to serve predictions to your apps. Okay? So that's the big picture. And if we zoom in on your algo and your model options when it comes to using SageMaker, okay, so once again, you can pick from a list of built-in algos, and this is the ones I'm going to talk about today. But please be aware that you can also use, you can bring your own script, bring your own training code for MXNet and TensorFlow, and my colleague Guy Ernest has a session later this afternoon on TensorFlow. So I think he's going to dive quite deep on TensorFlow here. You can also integrate SageMaker on Apache Spark. Okay, so if you do machine learning on Spark, if you have Spark pipelines, you can actually add SageMaker steps to your machine learning pipeline. And last but not least, if you have any other kind of requirement, let's say you want to use a deep learning library that isn't supported yet by SageMaker, or you want to bring your own custom code for training and prediction because that's what you built over the years, then you encapsulate all of that into a Docker container, and SageMaker is going to use that. Okay? But I'm going to focus on that left-hand side thing. So the purpose of those algos is simply to be 10 times better than whatever else is available today. That's the target, that's the goal we set for ourselves. And you will see in some cases we hit, and actually we do exceed that 10x improvement. So we have a few key principles here, and it's important to understand them. First of all, those algos are streaming algos. Okay, so typical machine learning algos will maybe load the whole data set in memory and then process it, which pretty much restricts how big your data set can be. Or they're going to load from disk and fill memory and move on to the next batch, etc., etc. And again, this is not the fastest and most efficient way to train. So we use streaming algos, and we'll see what benefits this brings. We just generally want to train faster. We want to train in a single pass, and that's another streaming benefit. Those algos will only see a data point once and change their internal state to reflect that, so they don't need to see data again and again and again and again to learn from it. This will yield really good reliability, even if we have crazy big data sets. You could have terabytes, tens of terabytes, hundreds of terabytes. It doesn't really matter because, again, we're streaming data, we're not loading it. And, well, we try to provide as much choice as possible when it comes to algorithms. So, we try to put our money where our mouth is, and we call them infinitely scalable algorithms. And this collection of algorithms that I will present has been implemented by Amazon, and it's being used every day by Amazon and AWS internally, for our own purposes. So like I said, we're streaming data to the algos, okay? So every single data point in your data set will only be seen once by the algo. And that's, again, the only way you could work with arbitrarily large data sets. There is no limit to the amount of data that this algorithm can support, can process, because we're streaming data through the algos, managing the state and building the model. So the benefit from that is memory consumption is now completely independent of the data set size, right? Because we don't have to load stuff in memory before we can train on it. We can just stream the data through the algo, and the algo learns as it goes, right? So there is no limit, again, to the size. When it comes to time and cost, well, it's going to be fully linear, right? The cost to train on 10 terabytes and the time to train on 10 terabytes will just be 10 times the cost and the time to train on 1 terabyte. So even if you go to petabyte scale data sets, it will just go linearly and scale linearly. You will not experience any kind of degradation. Obviously, when you talk about data sets this large, distributed training is important, and these algos support that. So we can actually split the data set across multiple instances. And once again, these will be fully managed by SageMaker. You just fire them up, and they do their job, and then they terminate automatically. You don't have to manage them at all. So each instance is going to work on its own part of the data set, managing its own local state. And then we have a component that's going to actually make sure that the different local states are consolidated into a shared state. Okay, so we can do distributed training at scale, and again, there's no limit probably to the amount of GPU or CPU instances you could fire up for a given job, okay, giving you even more speed for training speed for large data sets. And so the results of this is you don't have to accept any trade-off, right? Typically, you're probably in a situation like that dotted blue line, right? You have to compromise between cost and training speed. So if you want to train super fast, you need to throw a lot of hardware at the problem, okay? And that's going to probably cost more, just way more. There's a premium to that speed up. And if you have a small budget, then the only thing you can do is accept slower training times, right? But SageMaker actually, with the built-in algos and the performance that they bring, SageMaker really lowers the cost, and it stays linear for a very long time, right? So, and almost flat, as you can see. So you can actually get extreme speed up with those built-in algos without your costs increasing like they would increase with other solutions, okay? Because once again, the streaming nature of these algorithms, the fact that they support distributed training will let you just scale at flat cost unless you really, really want, very, very low training times like minutes. And then, yes, maybe it increases a bit. But moving from weeks to days is not going to require a significant increase of your training budget. So let's look at some examples. Okay, and we're going to take some time because I know these are pretty heavy slides. So the first algo is probably the king of all machine learning algos. It's called linear regression. And so we have an implementation of this. So here, we tested it on 2 data sets, a URL data set and a spam data set, okay? So what you need to compare here is the green line versus the purple line, right? And as you can see, there is a huge cost reduction when you train with SageMaker, right? It's pretty fast, and you never actually end up training for a long time. And if you compare the orange one with the light blue one, it's pretty much the same story, right? These are reasonably large data sets, And not only is SageMaker faster, it's significantly cheaper as well, right? So you win on both counts, which is not typical, because usually we always knew that there was this trade-off between time and cost, right? So one or the other, but actually here we can get both, and that's not typical. If we look at accuracy, because accuracy would not mean SageMaker would not mean anything. It was inexpensive and fast, but imprecise. If we look at a regression model for linear regression, well, we can see actually, we're comparable to other implementations, even though we stream data, which is quite different. And when we run a classification task, again, we're doing quite okay. We're pretty close to and even exceed the accuracy of reference implementations. Okay, so this example here, in a nutshell, tells you you will train at least five times faster, right? If we compare that, you don't see my pointer here, that rightmost purple point to the rightmost green point. That's really the same data point, right? So it's, let's say, 6-7 minutes on SageMaker and maybe 27 minutes with the other technology. And cost is 2 to 3 times lower as well. Okay, so very, very efficient. Here's another one, factorization machine, which is a generalization of linear regression. And don't be scared by the equations here. So factorization machines are popular for building recommendation engines, and I'll show you a demo in a few minutes. So here we trained on 1 terabyte of advertising data, trying to do click prediction. Okay, and that's not an easy problem. It's one of the harder problems. Okay, and we tested it on 10 machines, 20 machines, all the way to 50 machines. Okay, and you can see the cost is almost completely flat. Okay, and you have pretty much linear scaling as well, right? It takes almost 8 minutes on 10 machines, a little less. It takes about 4 minutes on 20 machines. It takes 2 minutes on 40 machines. So as you double hardware, you divide by 2 your training time. Okay, so flat cost and perfectly linear scaling. Okay, very cool. If we look at precision again, if we look at loss and the F1 score, which is a measure of how well our classifier is doing, well, we can see they're, again, very close or even better than reference implementations who would train for much, much longer, right? So in very little time, we actually get to almost state-of-the-art results. Okay, so let's quickly look what it means to use one of those. So I'm not going to go through every single line of code. I will share the links to those demos, and you can read them in detail, okay? Because I really want to go through everything here. So this is a notebook instance. I have my Jupyter notebook. I'm using a famous data set for movie recommendation called Movie Lens. You're probably familiar with it. So first of all, of course, I need to download it. Okay, and this is how it looks. Okay, so the first column is a user ID. The second column is a movie ID. And the third column is a rating between 1 and 5. And the last column is a timestamp, and I'm just ignoring it. Okay, so this is what I would like to build a recommender on. Okay, so I need to import some Python libraries here, including the SageMaker SDK. It's a Python SDK. It's available on GitHub. It's obviously pre-installed here. Okay, so in this data set, I've got just under 1,000 users, about 1,600, 1,700 movies, and I've got about 100,000 ratings, actually. So the data set is split between test and training. Okay, so I just need to load them from file into a dictionary here. That's strictly Python stuff. We don't really care. Okay, so I need to load my 2 data sets from the files into memory. I'm going to check the sizes here. So I've got over 90K samples for training here, and I've got about 10K samples for testing. Okay? Okay, so now my data set is loaded, and what I want to do is put it in S3, because this is where SageMaker will pick it up. But as we work with built-in algos, we have to make sure we provide the data in a format that the algo understands. Okay, so it's in the documentation. This factorization machines implementation expects data to be in protobuf format, which is a popular serialization format. So I need to take my Python data, my training set, and I need to write it to the protobuf format and copy it to S3. And that's what I'm doing in that next cell. Okay, using a SageMaker a function called write sparse matrix to sparse tensor. Copy that stuff into a local buffer, and then upload that to S3. Okay, and I do this both for the training set and the test set. Okay, so now my data is in S3. It's in the right format that the algo expects. I can get on with my training job. So you heard me say containers, 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 right? It's like, yeah, I really mean containers, like in Docker containers, okay? Because all the prediction, all the training and prediction work here under the hood happens using Docker containers, okay? So SageMaker right now is available in those 4 regions. So I need to select the factorization machines container that corresponds to the region I'm running in. I'm running in the US region here, okay? And I'm going to create that estimator object, which is in the SageMaker SDK, passing the actual container, storing the code, okay, for factorization machines. And once again, as you see, we don't write a single line of machine learning code. We pick an off-the-shelf container, storing that implementation. We pass a role, we pass the session, we pass the output prefix, which is where SageMaker should copy the trained model. And when it comes to training infrastructure, the only thing that we have to say is please train on one C4XL instance. That's it. You don't have to start any kind of infrastructure. You don't have to manage it. You don't have to install anything. You tell it, OK, please just give me one C4XL. And if I said, hey, please give me 10, I would just put 10 instead of 1. Right? If I wanted P3 instances, I would just replace C4 by P3, and that's it. Okay? So machine learning at scale, 0 infrastructure work. Literally 0. Okay? Then I need to set some hyperparameters for my job. These are algo specific, so I'm not going to go into the theory of factorization machines. You would run away, but these are documented. I want to build a classifier, blah, 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 blah. And then I call that last API fit, okay, which is the one that gets the training going. Okay? That's it. The rest is just my training log. Okay? So it's gonna it runs for a bit, and then I get my model. Okay? And the next thing I want to do is maybe run some predictions. So would it be complicated to actually take this model and deploy it on a web server somewhere, or many web servers that can serve predictions? Well, it's as complicated as this, again, called deploy, the deploy API on that model, and say, please deploy on a C4XL, job done, right? If you tried doing the same thing manually, using any of those machine learning or deploying libraries, building a web app to encapsulate your model and serve some predictions, you know it's a lot of work, okay? Here, it's just one API call, and you can predict, okay? And then I've got an HTTP endpoint that I can invoke and predict some new samples with it, okay? When I say 0 infrastructure, I mean 0. Okay? So I've got a detailed blog post on this. You'll get the slides, of course, and you can go through all the steps and run this yourself. Let's move on to another algo. This one is the k-means clustering algo. So it's unsupervised learning. Just pass a lot of data points and ask the algo to cluster them, to group them into a number of clusters. So here, once again, we compared this implementation to the best implementation we could find out there. And as you can see, the billable time in minutes, so the actual cost and time again, which is the same thing for us, because you pay for this by seconds, right? So time and cost are strictly equivalent for SageMaker. Well, we see that there is a huge cost reduction for the building, for the training of those clusters, right? And we see some good scalability as well, because when we move from 10 clusters to 500 clusters, there's a bit of a bump, but nothing like the other one. Okay, and when it comes to precision, the numbers that you see here are the actual, the total sum of square distances, sorry, the total sum of square distances between the points and their respective center, okay, which is how clustering works. And we can see that for pretty much every configuration, we either really close or we even exceed that best implementation. And more interestingly, when we move to very large data sets, like the two lower ones for advertising and the synthetic one, when we move to big data sets, the other solution crops out, right? We can't even train, okay? And SageMaker just goes on, and it would go on forever, because again, we're streaming data, so it doesn't matter how large the data set is. Here's another one. It's the godfather of machine learning algos. It's called PCA, and PCA is used to reduce dimensionality. So let's say you have 1,000 features in your data set, and that's way too much, and you want to automatically reduce that to 50, 10, whatever number of features is really needed for your model, removing correlation, etc. That's what PCA does. Okay, so here again, we tested it. There are two modes for it, deterministic and randomized, but never mind. And this is very spectacular, right? The speed up and the cost is just insanely lower using our own implementation compared to the best implementation that you're looking at here, the blue one, okay? And when you look at throughput and scalability, well, you can see that as we add machines, right, for the green and the orange bars, as we add machines, we maintain the same level of throughput, right? So more hardware maintains the same throughput, the same amount of data we can process with PCA, okay? So if you want to go faster, just add more machines. It will go faster and scale linearly. Another one, this one is neural topic modeling. It's a popular way. It's a popular algo for natural language processing, and you could build topics with it, like Comprehend does. And here again, we tried it against the best implementation we could find, and it gets to a significantly lower perplexity. Perplexity is the quality measure you use when you're working with natural language processing, right? When you do translations or you build topics. Okay, so we get 20% better perplexity, which is a very significant performance improvement. It goes on. So this is one of the newer ones called Deep AR, and you can work with time series. Okay, so a time series is a popular use case. So here we tried it on traffic data, electricity data, website traffic, etc. And we compared it to the best implementation we could find out there, which is using the R language, right? And well, as you can see, we get, again, we tend to beat pretty much all the time the reference implementation, just delivering lower percentage error and lower loss. So this is not only a super accurate algo, it's a super scalable algo, right? That's what you want. You want something scalable, something inexpensive, and something accurate, right? And we always knew, remember, that iron triangle? Cost, quality, and budget, pick two. Yeah, it's the #1 rule in project management. You can't have all three. Well, somebody worked some magic, because here, for those algos, we seem to be getting all three. We maintain quality while cutting significantly training times, and thus the spend associated. So yeah, it's a bit of a magic service, this one. So actually, DeepAR has been it's been invented by Amazon and AWS engineers. The research paper is available out there if you want to read it. It's pretty involved, but if you're into the computer science side of things and machine learning, you're going to like that. Okay, so not only popular algos like linear regression and factorization machines, but also new stuff that we invented. Okay, let's quickly look at a demo here. Moving on to a new notebook. Whoops. Okay, so here I'm using a data set from Berkeley University. This data set has a global temperature measure for the globe every day since 1880. Okay? And so I'm going to build time series, one time series for each year. So hopefully 365 points per time series. And I want to learn from that and predict from that. Okay? That's what I'm trying to do. So once again, I need to download my data set. Nothing spectacular. So it goes from 1880 to 2014. And I want to be able to predict 30 days, right? When you work with time series, one important parameter is how long is the time series that you want to predict. Okay, so here, at any given point in my time series, I would be able to say, okay, give me the temperature for the next 30 days. Okay, it's a parameter that I picked. Okay, so I will load my data once again, put it in a dictionary, blah, 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 Python stuff. I want to plot it. Okay, this is what it looks like. World temperature from 1880 to 2014. So you come up with your own conclusions, right? I'm not here to talk about politics. And then, so I need to prepare my data set for training. Okay, so the way you train on time series is a bit different than traditional machine learning data sets. The training set will be all the time series minus the last 30 days. Okay, so I will actually cut the month of December, okay, from all those years, and the test set is the full data set. Okay, that's how you work with time series. So I have to prepare for that. Okay, once again, I need to write my data set in a format that the algo understands. In this case, DeepAR expects JSON data, JSON lines. So one line for each year, as you can see, with the full 365 temperature for that year. Okay, so I need to convert my data to that format and write it to S3, basically. Okay, upload it to S3, like I'm doing here. And then once again, I can configure my training job. So same story, exact same story as before. I'm going to pick the DeepAR container for the region I'm running in, the role, the output path, blah, blah, blah. And I'm just asking here to train on one C4 8XL instance. I'm going to say it again, you're going to get tired of it, but it's zero infrastructure work. Then I need to define some parameters for my job. Once again, these are algo specific. The time frec parameter says I am working with daily series, right? I've got one data point per day. The context, the prediction length is the number of days I want to predict, so 30 days. And then I've got some crazy machine learning parameters. And you can read about those in the doc, okay? I set those parameters. I define where my training set and my test set live. And then I just call fit, and I'm training again, okay? And after a while, I get to the end of training, and now I want to do some predictions. So I'm going to save that model into SageMaker using the, oh, sorry, I saved it before. So here I'm deploying the model. So I'm creating a deployment configuration. It's called an endpoint configuration with one M4XL instance. Okay, and then I'm creating, using that real-time predictor object, I'm creating my actual endpoint. Okay, so this will fire up the M4XL instance, pull the container to it, deploy my model, etc., etc. So now I could predict. So I need to build a prediction request with that same JSON format that the algo understands. Okay, and some utility functions. Okay, and let's just look at this one really quick. So I want to compare my predictions with the actual value. So here I use 1984, right? And I'm comparing the last 30 days of 1984 with the values that I predict. Okay, so the actual the real values are the purple values here, right? The truth. Okay, and then when you predict with time series, you don't just predict one data point. You actually predict many different data points, and then statistically you can compute the 19th percentile, the 10th percentile, the mean, etc., etc. So that's what I'm doing here. Okay, so I see the mean is the blue line, and it's quite close to my purple line. So I'm actually doing a pretty good job at learning here. And the yellow and green channel are the 10th percentile and the 19th percentile. And the red line is just one of those samples that I predicted. I selected a random one. Okay? So my prediction is not too bad, right? And remember, 1984, he who controls the past controls the future. Right? That's what time series are all about. Okay? All right, so time series, not too difficult. So that's pretty good, right? This collection of infinitely scalable algos. But customers wanted more, right? You always want more. So we decided to add more algos to SageMaker, more built-in algos. So these are not infinitely scalable. These are not based on the same design principles that I mentioned before. But they're still quite good, and they're pretty useful. So let's look at some use cases. One of those is called LDA. And LDA is another topic modeling algo. And this is actually the algo that Amazon Comprehend uses. Okay, remember we talked about this one this morning, and Ian is going to do a cool session on Comprehend after this, I think. And well, in a nutshell, this is the algo that's being used. So if you wanted to build your own topic modeling application, you could try this. Okay, so here once again you have to compare the orange one with the light blue one. Okay, and you see on the number of topics that training time is much lower than the reference implementation. And you see, it's fair to say the scalability is quite linear, but there's obviously much more work involved in building 100 topics than 20. Okay, so it's more costly, but it scales pretty well. And then if you compare the green one to the purple one, it's about the same thing. Okay, so just the training time is just so much lower, right? Look at the scale over there, right? Each square is 50 minutes. So we literally save hours, right, on each job here. Well, this is the one that everybody uses, I guess. XGBoost. It's probably the most common classifier out there to do binary classification or multi-class classification. It's an open source project. So we just took that, probably tweaked it a bit, and now it's available as a built-in algo on AWS. Okay? And as you can see here, once again, we see almost linear scaling when it comes to a number of machines versus throughput. Okay? So if you just want to go twice faster and you add twice number of machines, you'll be pretty close to linear scalability. Okay? Super popular algo. I'm sure some people here are using this. Another one, it's called sequence to sequence. It's a natural language processing algo, and we use it for neural machine translation. Actually, last year we published an open source project called Sockeye, and Sockeye lets you train translation models. So once again, if you wanted to translate, again, let's say Hebrew to Russian, which is not available inside of Amazon Translate for now, well, you could probably try to build a model using sequence to sequence on Amazon SageMaker, or you could go and grab the Sockeye open source project if you didn't want to use an AWS service, and you could run Sockeye even on your own machines and train your model. Okay, so this is based on Sockeye, and Amazon Translate is also based on this. So many options to get to the same result. So as you can see, how good is that thing? It's pretty good. When it comes to measuring translation quality, our researchers use the BLEU score. It's a quality metric. And here, training English to German, depending on the instance size that we use, obviously, we get reasonably quickly to the state-of-the-art results. And in some cases, it's fair to say we slightly exceeded, but okay, I don't want to brag. So Sokai again has been published. Okay, so you can grab that article, and of course you can grab the sources on GitHub. Okay, this is Amazon invented, and we're happy to share it with everybody. Okay, one more. Yeah, I've got some more time. Image classification. So image classification is pretty much what you could do with Amazon recognition, okay? Except, like I said earlier, if you need to classify very domain-specific images, medical images, car part images, whatever, just specific things, it's fair to say recognition is not going to do a very good job at that because it's been only trained on general data. So here, we bring you a built-in algo. It's based on the ResNet architecture. So ResNet is a state-of-the-art image classification deep learning model. So what you do here, I'm going to show you a demo in a second. You can just grab that container and select a model and get to work, right? You don't have to actually design anything, just like in the other cases. And when we look at performance, once again, we see almost linear scaling, okay, which is very desirable if you want to train on a huge data set. Okay, so really quick. How would we do this? Okay, import some stuff. Well, now you know the story. I'm just going to repeat myself. Select a container, okay, in the region where I'm running. Okay, so here I'm not going to train from scratch my image classifier. I'm going to take a pre-trained network, a pre-trained version of ResNet, and I'm just going to fine-tune it, just to train it a little more on another image data set. Okay? So I need to download that data set, put everything in S3, define some parameters for the ResNet model. Okay? Put all that stuff in a JSON document, blah, blah, blah. Create my training job, okay? And this is the low-level SageMaker API, so it has a little more code, but it's a little more flexible at times, right? So you don't use that estimator object that I showed you before, but it's the same thing. So you create the training job, and then you wait for training to complete. Okay, I can grab the training information from CloudWatch logs. Okay, so the training accuracy, the validation accuracy, plot everything. I just trained for 10 epochs, which is very short, but I remember I was only fine-tuning, not training from scratch. And then once again, I can create an endpoint configuration. So I'm going to deploy to one M4XL, creating the endpoint, right? And now I can run some predictions. So I can grab some random images from the web, okay? In this case, a truck, and predict them with my model. And my model has 10 classes, including trucks, and I get 99.9% confidence this is actually a truck. Okay? So again, deep learning at scale, image classification at scale. You didn't write a line of machine learning code, just helper code to configure and run the training job. There's another one that got added recently. It's called Blazing Text. It's another natural language processing algorithm. It builds word vectors, which is a popular technique for a lot of NLP applications. There are some benchmarks against fast text, which is Facebook's implementation, and they're quite good, right? I didn't want to add more stuff to this presentation, but if you work with NLP models, NLP apps, this is, once again, a very, very scalable way on using distributed training and multiple GPUs to build word embeddings at scale. Okay? All right, some resources. So obviously the machine learning website, the AI blog that has a lot of code and customer stories, etc. the SageMaker service page, and there's a free tier available for SageMaker, so you can go and actually try it for free. There are a lot of notebook examples on GitHub, so you can also find them on the notebook instances that you fire up in SageMaker. But if you just want to read them quickly, just go to GitHub and look at for all these algos, and of course all the other ways you can use SageMaker. And again, Guy will talk about that later today. If you'd like to see more about SageMaker, I recorded a YouTube video showing you the different ways you can use it. So built-in algo, bring your own code, bring your own model, bring your own container. Seems to be quite popular, so probably you'll like that. And well, finally, I'm blogging on Medium, posting some quite a lot of stuff actually on machine learning, deep learning, Apache MXNet, SageMaker, etc. And actually, the 3 demos I showed you today are straight out of that blog. So again, you might enjoy that. Okay? Well, thanks again. Thank you very much.